Okay. Can somebody confirm that you can hear me?
We can hear you and see your screen.
Yep, we got it.
Okay. Before we get started, and I just posted this, I don't know, 20 minutes ago. Chapter 4, two-dimensional steady state heat conduction. So these are some new PowerPoint slides. Okay. One is that I have posted review paper number 2. Let's see, I think you have about 2 weeks to do it. And I believe you just turned in a homework set, and I should have another homework set started for you tomorrow. And I've already tried to think about what we're going to cover in that homework set. Anyway, I have my list. I can't think about it now because I'm already thinking about two-dimensional heat conduction, but I'll have a homework set ready relatively soon. Okay. 2, I have confirmation that I can leave your exams on Luann Graham's desk, and I am going to commit to having them there by 10 a.m. tomorrow. Do people? So I am actually not sure where Luann's desk is. I have some instructions, but is there anybody else who doesn't know where it is? I kind of have some instructions. I think I'll find it tomorrow. If you don't know, I mean, try asking another classmate, because until I've been there, I don't know that I'm going to have a good plan for you. Okay. I'm going to ask, I'm going to try and do something to make it not so easy that you flip through paper and the papers and find yours. They'll be in alphabetical order, but that you can see other people's scores. So I'm going to try and cover them up a little bit. But I'm also going to ask that you have some, I'll tell you what the average is. Oh, and I forgot to look that up. I'll have it written down what the average is, so you'll know that. And I would ask that you take your paper out, but that you don't browse through other people's exams. The scores are supposed to be confidential. And so, again, there's a little bit of heartache for leaving them unattended, but I think that it should be okay. I think you guys are responsible, and you're probably thinking, I don't want other people seeing my work, so I will, pick mine up and leave the others for the next person to come get them. Okay. Third thing, has anybody looked at their homework 2 feedback on Gradescope?
Yeah. Yep.
Yes. Okay. So part of it, and I guess I can't exactly ask you. So if you got full credit, you maybe didn't see any little notes, but I tried to make some comments. Mostly, I would say scores were pretty high. There were a few things, small things, generally not huge, that were missing, and I tried to let you know what those were. I'm not sure how often you guys feel good about speaking up. But send me an email if you have a concern that you think you're not, I don't know, you're not getting enough feedback, there's points taken off, and you don't know why. Okay, so you just did your 4th one in Gradescope. It's not been as wonderful as I had hoped, because I really wish there was a way for me to write in pen and put something where your errors are. But maybe this is this is kind of what it's going to be for until we meet in person. Okay, if you are looking at the syllabus, I think I'm maybe 4 classes behind. So I can see a few ways to pick up some pace, and I may try and work a little bit faster. But we're going to talk a little bit about two-dimensional steady-state heat conduction. Okay. And I would like you thinking about in Cartesian coordinates, maybe that should be a capital. And I normally think of not having volumetric heat generation, but I guess I didn't state that there. But we're picturing temperatures now, not just a function of X. We've been doing that so often. We say one-dimensional conduction. Now temperature may be a function of 2 coordinates. And if we're in Cartesian, it might be X and Y. This two-dimensional section could be applied in radial coordinates, spherical coordinates too, but I think it's easiest, for me at least, in thinking about the X and Y. There are 3 broad classifications of solutions: graphical methods, numerical methods, and analytical methods. And as I tell you graphical methods, and we're going to talk for a minute about flux plots, and you can already see the little heading down there. Graphical methods are not used now that we have, higher powered computational methods. But I like to mention it. And really, graphical methods, in my mind, kind of leads into shape factors, which people aren't doing graphical methods anymore to come up with shape factors, but it's really a very simple transition to then think about shape factors. Numerical methods. So there's a number of methods under that category. So a little bit finite difference, which is what our book presents, and that's always like the first, when you're starting to talk about numerical methods, finite difference is kind of easy one to get into numerical methods. And then finite element, and that's, you may take a course in that, but I would say it's often more common that people just use finite element methods. So it's gotten to be so common that you don't always need to know some of the details behind it. Okay. And then another one that I don't think is very common, it's maybe a little bit more research oriented, but there are boundary element methods that can be used to do numerical solutions to conduction problems. Okay. And then the very last dot there is analytical methods. And that one I need to just talk about very briefly. You have to have pretty simple coordinates set up. And then there are some analytical solutions. And it requires separation of variables. And we can see Bessel functions appear again. So we'll just mention that one. Analytical methods maybe aren't as widely used anymore, but I'm going to tell you, people who do numerical methods, when they're trying to demonstrate that their code works, they're always looking for an analytical method that they can apply that numerical technique to. And so, yeah, see, I can solve this analytical, so something to compare to validate. And then they move on and do some other things that there's not an analytical case for. So analytical methods, I don't know, in industry, maybe people don't use it. But again, people who are trying to develop some numerical methods are always looking for something to compare to. Okay. Graphical methods or flux plots. The utility is that it requires delineation of isotherms and heat flow lines and provides quick means of estimating the rate of heat flow. And the procedure is that you construct nearly perpendicular isotherms and heat flow lines to achieve a network of curvilinear squares. And then I listed some rules. On a schematic of the two-dimensional conduction domain, identify all lines of symmetry, which are equivalent to adiabats and hence heat flow lines. Sketch approximately uniform spaced isotherms on the schematic, choosing a small to moderate number in accordance with the desired fineness of the network and rendering them approximately perpendicular to all adiabats at points of intersection. And the third one, draw heat flow lines in accordance with requirements for a network of curvilinear squares. All right, that's a lot of words. Here is an example. Picture this as a square-walled, I don't know, two-dimensional. So we want maybe some hot fluid just passing on the inside, and we got ambient air on the outside. And so they're showing temperature 1 and temperature 2 along these two different surfaces. So one of the things is to really look at what the geometry of this two-dimensional system is. And then they have shown that due to symmetry, these dashed lines are adiabatic lines, which behave like insulated surfaces. And so to save some time, we don't sketch any more of this square channel. We're just going to look at 1/8 of this. And they've sketched these symmetry lines as insulated surfaces. Then it says to think about sketching lines of constant temperature. And we already have two lines of constant temperature because we are given T1 and T2. You know, it's not listed in the rules up above, but, you know, if you were really doing this precisely, and this one's already sketched out, but if I was starting from scratch, I was trying to come up with these lines, you would want to do this on something where you can make revisions and keep trying to get the spacing correct. You kind of have this idea that since we're getting wider over here, that I'm going to draw my isotherms getting wider as I move towards T2, but you're not going to get that perfect. And I always want to mention this, but I don't know why, because it just makes me seem like I'm ancient. But when I took heat transfer, we actually did some, and they were very clear to tell us, do it in pencil, because you're going to erase it, and you're going to try again, and you're going to erase it and try again. But here we are. I'm sketching in. So this is another line of constant temperature, another line. All right, so I won't keep sketching those in, but some lines of constant temperature. And then we know that conduction happens. It wants to move in the direction of the highest temperature change. So it wants to be normal to these isotherms. So now we're drawing these heat flow lanes. And they've got that one sketched in there. We'd like to make these heat flow lanes perpendicular to the lines of constant temperature. Again, we're thinking about, again, heat wants to flow in the direction of the highest temperature gradient. So it wants to go normal to those lanes. Okay, so we'll sketch a few more in. Okay. And again, all of these, we're trying to do our best to make these nearly equal length boxes. So if I think of these four sides, I'd like to have all of them have the same length. All right. We get to this guy out here, it's pretty far off, pretty skewed. That's about the best we can do. So what good is this? There is something called a shape factor. And it's a conduction shape factor, and it is defined as M times L divided by N, where M is equal to number of heat flow lanes and in our picture, so this is heat flow lanes going this direction, and I have 5 of them. And N is the number of temperature increments. So a number of temperature increments, 1, 2, 3, 4, 5, 6. Okay. And L is the depth into the page. And then the way that I would use this shape factor is again, it's all about the geometry of this problem. So how this heat flux plot comes out. And then K is thermal conductivity, and then the driving temperature difference.
I have a quick question.
Yes?
So it seems to me that these, I guess the number of lanes and the number of heat or temperature increments is fairly arbitrary. You can just choose to add more or less. How does that affect the actual calculated heat transfer if that's changing the shape factor?
Okay. So without doing another one of these, if I made finer spacing, then both of them have to become, again, we're trying to make each of these lines about the same length. So if I split this guy into 2, then I end up splitting the temperature increment in 2. So because I'm trying to make these squares equal length. So again, we got tiny ones here, we got bigger ones out here. If you were good at this, you could pick any spacing, but it's then going to dictate, if I pick more temperature increments, I'm going to have more heat flow lanes. It's this ratio that if you're good at drawing these flux plots, that ratio is going to be the same, whether you do small separations or bigger separations.
Okay, thanks.
All right. I was here yesterday and I keep trying to think of more things that make you think about flux plots. So this was a video, and the person was applying a voltage at certain locations and drawing lines of constant potential. So actually had a voltmeter to sketch these white lines. And, you know, they're not perfect, so he got close. And then, well, I'm trying to think of how they did these red lines. But this looks like the flux plot. Again, it's the electrical analogy to heat transfer, that we have current flowing, and then we have these white equipotential lines that give us lines of constant voltage. Okay, and some of the equations we have for heat transfer end up looking like some of the equations for electric fields and magnetic fields. So besides thinking about these flux plots, there are shape factors that have already been developed. So we already talked about the shape factor. It's given symbol capital S. If we wanted to write a thermal resistance element for a conduction shape factor, we could write it as the reciprocal of the shape factor and thermal conductivity, just so that you're thinking about this idea that I could put a shape factor as a combination with other resistance elements. All right, I think these bullets are going to finish off what I wanted to say. There are a selection of shape factors given in table 4.1 of Bergman and Levine, so that's our book. And there is a handbook of heat transfer that has way more shape factors given. Okay. No, I've never been like a total fan of shape factors. I mention them because there could be a case that is exactly your case and could solve many, could make your life way easier. But, some of the things, so this is only applied for steady state. Let's see, I'll make a note over here. And you have to be working between two faces of constant temperature. So just thinking about up here, we had to know a constant temperature on one face and a constant temperature on the other face. But again, there could be a case you find in this list of shape factors that hits the need that you have for a given geometry. So I won't have you do a flux plot, never on an exam. Let's say that. Maybe if I came up with a cool problem, we might try it for homework, but I kind of like the idea of thinking about what the lines of constant temperature look like and the heat flow lanes. Okay. We're going to look at this problem. Has a 0.25 meter diameter hole, is drilled through the center of a block with dimensions 1 meter by 1 meter and through the full 10 meter length. The convection condition for the outer and inner surfaces are given in the diagram. Okay. So we're saying in this hole, we've got a free stream temperature of 300, and we have a heat transfer coefficient. And then the outer free stream temperature is 25, and it's got a low heat transfer coefficient. And they tell us the thermal conductivity for this material. And the question is, for steady state conditions, how much heat is lost from the hot fluid flowing through the inner hole, and the temperatures T1 and T2. Okay. We're going to start with this solving for the steady state heat transfer. Okay. So we're going to have two-dimensional conduction. It's conduction in that our temperature is going to vary in that plane we see, but it's not going to vary out of the page. So just function of temperature function of two coordinates. Boy, we could add constant properties. We always do that. It just says that thermal conductivity is a constant. Our sum of thermal resistances, it's going to be a convection to this circular inner wall, and then we got conduction through this sort of block, and then we got convection off of the surface. Okay. We've seen this one before, how we would handle convection, and we know the heat transfer coefficient. And we know the area of this is going to be pi, a 0.25 meter diameter hole. Okay, so we're going to use the shape factor. That's the only very interesting part of this problem. And if we looked, there is in our book a case 6 shape factor. Okay, and it's exactly this case. If you looked at it, you'd see there's a constant temperature here. Oh yeah, constant temperature 1 and constant temperature 2 on the outer surface. Right. And it looks like S is equal to 2 pi L over natural log of 1.08 W. Oh, let me tell you what W is, D. Okay. So W is, and there's a little picture that goes with this case 6. So that's one side of this block. So W equals 1 meter. L is the 10 meters out, and we know diameter. Okay. For many of these shape factors, they give some things to check. And it's written beside the shape factor, and I checked those. This one is legitimate, or is valid to use for this case. So if I plug in numbers, I get X, or S is equal to 42.94 meters. Okay, and K is 150 watts per meter Kelvin. Okay, so we could put those numbers in, but that's our our conduction, and then our convection too. Okay, H2, that in is small, 4 watts meter squared K. And area is going to be 4 times 1 meter times 10 meters into the page. It turns out this is a really tiny resistance. Our conduction is tiny because we have such high thermal conductivity. But some of thermal resistances right, 8.72 kilowatts. Right. That seems like a lot, but we had a pretty big surface area. This thing is a meter by a meter. And then the next thing it asks for, but you have seen this before. Let's say we had to solve, for example, it says temperature at the inner hole. Ooh. If we were drawing this resistance network, which I did not do at the outset, but we had T infinity 1, T1, T2, T infinity 2. If I have to solve for T1, that just says I could do, now that we've got Q, is T infinity 1 minus T1 over, and now I'm just going to use our convection on the inside. So we've seen that before, and I've got T1 is 245.5 and I'm not going to show you, have the idea how we get T2. I'm only mentioning this, man, these are pretty close together. So that block of material has a pretty high thermal conductivity, so we didn't get much of a temperature difference. Between those two surfaces. Okay, so I think I mentioned shape factors are kind of niche-y to me, kind of specific cases. Numerical methods, this is going to be quite all-purpose, but we aren't going to spend much time on this. I always think if you have to do some heat conduction, some heat transfer analysis for very complicated systems, you are going to use a finite element tool. I like that you have seen finite difference and have some basic concepts about it. Okay, so numerical methods, I earlier mentioned that we have finite difference, finite element, and boundary element. Okay, nearly every heat transfer book shows a little bit of finite difference, and the reason is because it's pretty easy to implement. Okay. But then finite elements got to be so popular for using for stress analysis, for mechanical design kinds of things. And so it's a pretty easy extension to use that for heat transfer. So I'm going to say most packages, it's a little bit of overkill, but you're just going to use finite element method. And then we talked about boundary element. I'm just mentioning it. I don't see it used very often in practice, and I see it occasionally in research papers. One of the bonuses of it is that you don't need to have it, you need to have information around the boundary. So all of these other methods, we're going to be writing nodes throughout the whole field that we're interested in. And for this last method, you don't have to solve throughout the whole field. You're looking at the boundary. Okay, so we are only going to talk a little bit about finite different methods. They're in 4.4 of our textbook. So maybe my introduction here is I opened up by saying something about the equation we're trying to solve. Let's make it not even have volumetric heat generation. Okay. So if we're trying to solve the temperature field for two-dimensional steady state conduction, no volumetric heat generation, this is the equation we're trying to solve. That's our governing differential equation. And for finite difference methods, what we were trying to do is write these partial differentials in terms of particular nodes, particular points throughout this field that we're looking at. So what they're trying to show here is this big blob, and we have set this up in an even grid work. And then we write these partial differentials in terms of delta t's and delta x's. So this first equation that they have down here, and let's picture we're looking at this node. So in the x and y direction, we think of m index is changing as we move in the x direction, and the n index is moving as we change in the y direction. So to write the derivative of temperature in the x direction, and they're doing it at this halfway point, so between those nodes, maybe I'll make it look like a little X mark there. So they say Tm comma n, so that center node minus m minus 1, they go over here, and then the difference, the length scale over which that temperature variation occurs is delta x. And have we defined, so our node spacing in this case is going to be a delta x. Okay, they do the same thing looking at this location, and they write the second another temperature gradient, but at this new location, m plus a half comma n. All right, and then finally we want to get the second order. So I'm taking how this guy changes, so that gradient minus over delta x again. So this looks like I've taken d by dx of what I had in here. This is my dt dx. And now it applies right at that center node because I evaluated one at the m plus a half and one at the m minus a half. All right, and then if I put this together, what does it look like? Tm plus 1 comma n minus 2 Tm comma n plus Tm minus 1 comma m over delta x squared. So I like that you have this concept of, instead of, I have this analytical expression for the second derivative of temperature with respect to x. And what I'm rewriting that is in terms of particular node spacings. And I lose some precision. We may talk about that a little bit later in class of what we've lost in representing this as at these discrete locations. That's our representation. Okay. Oh, and we think of, there is a lot in this, a lot in numerical methods. We are choosing relatively small delta x's. So we do, again, if we chose big delta x's and we're trying to describe that temperature gradient, maybe we're not doing such a good job. But imagine we have small enough delta x's that we're doing a pretty good job of describing how the temperature varies across those nodes. Okay. This picture up here is showing how I would write these temperature gradients through for an internal node. And it involves the temperatures at the neighboring nodes. This next slide is to have you think a little bit about, eventually I got to get to boundaries, and that's where boundary conditions play a role in solving these problems. And if I looked at the equation, the finite difference equation I might use for a node that's on the boundary. So this one is now m plus n. So that's always our node of interest. And I've got convection occurring on that face. The way that I have shown this, and it seems very simplistic, is to think about always heat transfer is coming to the nodes, and this is how our book shows it too. And then writing these equations out in terms of temperatures and in terms of these little delta y's or delta x distances. And they have to sum up to zero. So an energy balance on this term, I don't have volumetric heat generation. So all the combination of all these terms coming in has to add up to zero. So if I was writing Q from the north, and generically I think of it as K, some kind of area, and I have to have dt dy, and then I want to put it more precisely for this case. So thermal conductivity, I have to know that for the material. And again, we're thinking I got more material up here. We're just looking at this one element sitting on the surface. Okay. So the area that I am conducting over, and they've shown it in this orange color, is a delta x over 2, and it's y, a depth 1 into the page. So that gives me an area. My delta t is going to be Tm comma n plus 1 minus Tm comma n. And my distance over which that delta t acts is a delta y. I think it's easiest to put together the north and the south because they're going to look a lot alike. So I have just writing out generically, but now I've got Q going in this direction. The area over which I am conducting heat, it's a delta x over 2, and I have a unit 1 into the page. And now the temperature difference, I always write it from the other node to the center node. Okay. Q east, generically, so just thinking about it, has the form of convection. So a T, I'm going to put infinity first, minus T surface. And now I want to write for this particular case, and it's a heat transfer, the area over which I am convecting heat that affects this orange blob that goes with that MN node. So it's the surface area is delta Y. And I have a 1 depth into the page. And then my temperature is T infinity minus Tm comma N. And Q from the west. So this is another one that is conduction. So in this direction, now my area over which I'm transferring heat is a whole delta Y and 1 into the page. And the temperature gradient is Tm minus 1 comma N minus Tm comma N. And now my distance over which that temperature difference acts is delta X. And then what I would do is I sum these terms up. And maybe there's some simplifications I can make. But what you end up with is for each node, you have an equation that is based on, I've got this unknown Tmn, but all of these temperatures are unknowns. So hopefully, like just looking at this one node, you can kind of think through how many unknowns appear in this equation. So I can't solve this explicitly. I have to keep writing these equations till I get a solvable system of equations. Okay. And then you got different tools you can use. Again, I think most often you are not going to choose this as your method. You're probably going to use a software package to solve your conduction analysis. But if you had a simple case, you know, I have seen people use finite difference to do some simple analysis. If you had to solve a system of equations, you can do some iterative approaches that aren't tricky, or you can have a simultaneous solver package that may do the solution in one step, no iteration required. This problem that I have selected to talk a little bit about a finite difference problem, what I wanted to bring out is one of the bonuses of finite difference. Okay. So this is a fin problem, 10 millimeter diameter rod, 250 millimeters long, has one end maintained at 100 degrees C. The surface of the rod is made of stainless steel, experiences free convection that is a function of the surface temperature. And the units for HC are watts per meter squared. Here's our equation for free convection. And if I was going to draw this, okay. And this find statement says, assuming one-dimensional conduction, calculate the rate of heat removal. Oh man, I got too many rates in there. The rate of heat removal from the rod. And I put those dots in. We'll talk about it in just a minute. I want to get my figure looking okay. But every time we have done a fin analysis, it's been a constant heat transfer coefficient. You know, all those times we use, you guys just turned it in, so you're probably like feeling, you know, you've seen plenty of fin heat transfer analysis, but we always picked a constant heat transfer coefficient. Okay, so we need to do something different if we're going to allow heat transfer to vary with temperature. And this is the idea that if I had some base temperature down here of 100 degrees C, that you imagine as temperature drops as I get towards the tip of this fin, that the convective heat transfer coefficient is not going to be as large as I move up to the tip of the fin. A way that we could handle that is using finite differences. And so I'm going to not do too many nodes because we're just going to look at this. But if I separate this into some equal chunks. Okay, and I'm going to keep this one as a base. This one can be 1, and this 2, and we can number them as we move to the tip of the fin. And let's think about writing a nodal equation for node 1. And we're thinking this is a circular cross section. So I'm going to take this slice out of this circular rod and looking at energy balance. All right. I'm following the convention that I'm making all of the heat transfer to node 1. So I do think it's unusual. We think about convection away, but I'll set up my equation appropriately. So for convection, we got a heat transfer, convective heat transfer coefficient. And I'm just going to call it H1 for right now. We know it's going to involve this equation. But it's going to be, so for H1, I'm going to substitute in temperature 1, which is unknown. So let's just put our H1 in there for right now. And I'm going to have surface area and T infinity minus T1. Okay, and we got to do something with surface area in a minute. And then from the east, K times cross-sectional area, and we'll write what that down is in a minute. But then I'm going to have T2 minus T1 over delta X, this separation in between nodes. And from the west. Okay. And all of that has to equal 0. So thinking through, I got, well, let's rewrite. So I'm substituting that in for H1. Surface area. I'm substituting in perimeter times delta X. Okay. Cross-sectional area is going to be pi over 4 diameter squared. Okay. So I think without going through this whole problem, the point I wanted to make is we're going to be able to, all of these temperatures are unknowns, right? We're going to set up, base temperature is known. We are going to be able to set up a system of equations. For us, it's going to be 5 equations because I have to write one for each of these knowns. And we're going to have these 5 unknown temperatures. But it doesn't matter. I mean, it makes the problem a little bit harder to solve, but this same unknown T1 appears in this equation for the heat transfer coefficient as this unknown I have to solve here anyway. So I can leave it as an unknown and solve for that precise temperature to allow the heat transfer coefficient to vary. Okay, so this one actually makes sense. I like this one pretty well, that we're thinking about for free convection, it's a function of this driving temperature difference. But another way we could do it is we could have thermal conductivity as a function of temperature. I mean, this one gave us a constant K, but I could put in an expression for K and have it varying as temperature. And again, I have to solve for T1, but if I set up my equation properly, I can solve for that T1. Okay, I did not show you all the details. Okay. But if we went through and solved this series of 5 equations, so this chart has the results. Base temperature is 100, and we see a pretty big drop in that first section. So we're down by 40 degrees, and then we see smaller and smaller temperature drops. Okay. And heat transfer coefficient, just so you see how much that's varying over the surface. This does give you an idea that what we're getting now is, you would imagine I'd have some nice equation, like heat transfer coefficient is varying as some curve. But really all this allows us to do is over increments, over the base, I have a heat transfer coefficient. Over that section associated with node 1, I have some constant value. So the downside of finite difference is we're not going to get some beautiful looking curve. We're going to get a value, and the way we use it, we say that holds over that whole node. If we wanted to do a better job, a more precise job, we would split this fin up into 20 nodes, and we could get a better estimate. So the last thing it asked for, so, we did some of the math we saw for the heat transfer, heat transfer coefficient along this node. It asked for heat removal from the base, or heat removal from the fin, so Q fin. Okay. And what I had to do was solve for the convection off of each section, each element of the fin. So I would take this first heat transfer coefficient for the base times the area, and I'm only scrolling up, have you thinking this is a delta X over 2 that is associated with the base. And then I take the temperature of the base minus T free stream. Plus, now I take H1. So that's saying what that heat transfer coefficient I calculated for the first node. And now it's perimeter, and it's a delta X and T1 minus T infinity. Okay, and I have to keep summing those up. And eventually I get to Q for the fin. Okay. All right, and I'm just going to mention this. All right. If you remember when we did fin analyses before, oh, I don't want to put the minus sign in there. Let's say K and dt dx. And I solved for, we could solve for the temperature gradient right at the base. So at x equals 0. And this is how we did it analytically. We had an expression for temperature. It doesn't work. It doesn't, it gives me a terrible estimate because every time I'm looking at, I've got these little temperature gradients between each node, and I'm doing a bad job of finding a temperature gradient right at that x equals 0 node. And I'll tell you, I tried a few things. It always gave me a bad estimate. And if I had a better, a good solution for this, I would tell you. But I ended up having to go back to, for finite difference, I could not get a good estimate of the temperature gradient, again, because we're just doing these little chunks of temperature gradient from base to 1, from 1 to 2. And did not allow me to use this method we use for analytical. So I thought that was interesting. I had to go back to, summing up for all of the convection off of these elements. All right, this last bit is to talk a little bit about these finite difference equations. Okay, this is a Taylor series expansion. And what we want to imagine is, now I'm looking at, and this U, it's just some variable. It could be temperature. We've been working way more with temperature gradients, but here is a U quantity. And we're looking at, how would I calculate this U quantity at X plus delta X? So I went to I moved to some new node. Okay. And what this is saying is that I would take u at my current location, x0, y0, and then I take the first order derivative. So how does u vary with x? Times delta x. So this is just saying evaluated how that slope is varied at x0, y0. Then I take the second order derivative, and it's got then multiplied by delta x squared over 2 factorial. And then the third derivative, and it's multiplied by an x cubed over 3 factorial. And I could keep adding more terms. Let's see. Oh, and in B, what did we do in B? So B says now I'm going the other direction. I'm at some x location, and I'm going an x minus delta x. Okay. And it looks very similar. It's just that I have some negative signs in front of the odd ordered terms. And it may have been a while since you've thought about Taylor series expansion, but I think this maybe vaguely looks familiar. So our goal is, we started out and said that we have these differential equations. We would like to come up with a way to express this differential equation in terms of particular locations. We're in terms of discrete locations. So here's our first order. Okay. So let's rearrange and get that first order partial derivative in terms of these locations. So this is rearranging equation A. Okay, so I'm going to have to subtract off. Want this guy on one side of the equation. I'm going to subtract u of x0, y0. Okay, so we're thinking those are our two discrete locations. And then I have to divide through, where is it? Okay, I got to divide through by delta x. Okay. That looks a whole lot like that equation we wrote, again, we did it for temperatures, but it was our dt dx. It was written at two locations, and then we had a delta x in the denominator. Okay, but the bit we left off that we didn't talk about before is that there are some higher order terms. So we got some other terms, and I'm only going to write the first one down. And then I have to remember, I divided through by a delta x. So we got a delta x, okay? And then we'd have this next order term, third order term. Okay. It's really the one that has the highest order that we care about. So I'm going to cancel out a delta x from the top and the bottom. And the way that this is written is that this term that we don't use, but we'd like to say something about dropping this higher order term, we say that this is a truncation error. it has error of order. Ooh, I want to put an order, an O here. So it's means order of delta x. If I took my third order term along, so if I took this guy, where is he? Well, let's put him in there just so we're thinking about this. Okay, and I got to divide through by delta x. So I get a second. Okay. The reason we care about this is this truncation or error would be of order, order delta x squared. And that is a smaller truncation error. You think of delta x as being these tiny, like 0.1, for example. And so to have it a error delta x means I've got a 0.1 error. But if I have a delta x squared, my truncation error is 0.01. So the biggest error for this first equation, it's of order delta x. I don't think I'm going to have time to show this. And like I said, I feel like we got to get moving on to transient. But what I would have liked to show you is that there are ways you can write this discretized equation. So I'm writing it in terms of, here it looks like a U, but could be a temperature at 2 nodes. That there are different ways to write these nodal equations that can reduce your truncation error. If I subtracted these two equations, that is an example, and then I solved for du dx, for example. That case, I get a truncation order of delta x squared. That is desirable. If you are doing numerical simulations, you are looking at ways to write these equations to reduce this truncation error. Okay, I'm nearly done. Let me write one more note here of why we started down this path. All right, that was a really brief introduction. You saw a little bit about, this truncation error, and I realized we didn't look at how you would formulate to get a smaller truncation error, but I'm going to end lecture for now. And as normal, I will hang out for a bit. I really tried to estimate that I could get your exams there by 10 o'clock, and I don't see how it could go wrong. I have somebody coming to do work at my house, and you're probably going, well, yeah, that's going to go wrong. But I can't imagine that they would take more than an hour. So I really feel like 10 o'clock is going to be a good estimate. Okay.
Thank you.
Professor, I did have a question about actually from like the very first slide,
Okay.
which is just like kind of in addition to all the mathematical models that you went over, do you ever use like scale models, like physical models of if you're trying to figure out how heat will flow through a certain shape of material, you just create a small